Good morning to all of you. Good morning. So, we were trying to understand the MH loop, magnetic hysteresis. So, इस तरह का जब भी ग्राफ आता है ना जिसमें ये आप एक एरिया अंडर द कर्व मिलेगा, ओवरऑल लूप जैसा बन जाता है, इसी को हिस्टेरेसिस कहते हैं। ठीक है। तो पैरामैग्नेटिक में कोई हिस्टेरेसिस नहीं था, एमएच लूप था, एमएच कर्व था, बट देयर वाज नो hysteresis. In ferromagnetic, you are getting this kind of फेरो फेरी, इन सब में आपको मिलेगा इस तरह का बिहेवियर, typical behavior. So this curve is important in identifying, practically speaking, when you follow this M versus H curve, you are able to identify whether something is ferromagnetic or not, ferromagnetic or paramagnetic. Okay. So, and the ferromagnetic is will also retain uh, magnetization to a good extent. So you can see the retention. This is the saturation MS, saturation magnetization, and this is the MR, magnetization that we call it remnant magnetization. So that remains even after the field has been removed and you are at zero. When applied field is zero, तब भी उसमें काफी high value of magnetization. So that is what happens in a permanent magnet. जो भी आप चुंबक लेके घर में यूज करते हैं या छोटे छोटे चीजें, वो सब ऐसा ही होता है. इट इज द रेमनेंट मैग्नेटाइजेशन. और इसी को हम कहते हैं कि वो इट रिमेम्बर्स, मतलब ये अपनी हिस्ट्री को याद रखा है कि मैक्सिमम जब इस पे फील्ड अप्लाई किया गया था, देन इट हैज, मतलब इसके पास इतनी, इट हैज हाई वैल्यू ऑफ मैग्नेटाइजेशन विच वाज सैचुरेशन. एंड जब हटा दिया तब भी वो लगभग, बहुत ज़्यादा अंतर नहीं है. सैचुरेशन मैग्नेटाइजेशन, ये जो जीरो फील्ड पे मैग्नेटाइजेशन है, लगभग उसी स्टेज. इसीलिए कहते हैं कि ये इट हैज़ अ टेंडेंसी टू रिमेम्बर व्हाट हैपेंड टू इट, इसको क्या हुआ था. और इसीलिए ये जो चीज़ है ना, जिसके पास भी ये रेमनेंट मैग्नेटाइजेशन ज़्यादा हो, इफ द डिफरेंस बिटवीन एम एस एंड एम आर इज लेस, मतलब you are able to retain whatever saturation, when the maximum magnetic field was applied, you got some high value of such magnetization, and that value is retained here. So such kind of substances are used for making memory devices. ये जो आप पेन ड्राइव, हार्ड ड्राइव, ये सब यूज करते हैं, सब कुछ इसी इसी पे हम यही ढूंढते हैं कि किस कौन सा मटेरियल होगा, जिस कैसा बनाएं. अगर हम केमिस्ट हैं या so material scientist or chemist will focus on making a material which will have high value of remnant magnetization. तो वो एक अच्छा मेमोरी डिवाइस बनाने के काम आएगा. तो यही चीज मेन आपको देखना पड़ता है कि जब भी, ठीक है, रिकॉर्डिंग मीडिया, टेप, सो एनीथिंग, स्टोरेज, हार्ड ड्राइव्स, पेन ड्राइव, सब में यही इस तरह के मटेरियल यूज होते हैं. ठीक है. और बाकी सारी चीजें हमने एक्सप्लेन की थी आपको कि देर आर टू थिंग्स दैट इज इम्पोर्टेंट. वन इज in the major part of the this M versus H plot, you have domain wall motion. There are two things that we found. एंड जैसे जैसे डोमेन वॉल मूव करता जाता है, कोई जो पहले से ही काफी क्लोजली अलाइन, नॉट परफेक्टली अलाइन, बट लगभग उसी एंगल पे आसपास है, वो वाला जो है ग्रो करता जा रहा है. देखिए ग्रो कर रहा है और फाइनली वो पूरा एक डोमेन हो जाता है. तो बाकी के सब श्रिंक करते जाते हैं. सो ऑल दिस इज हैपनिंग थ्रू द मोशन ऑफ डोमेन वॉल्स. सो यू कैन सी दैट दिस वॉल हैज मूव्ड. ये वाला वॉल, सारे वॉल्स जो उसकी बाउंड, मतलब द डोमेन विच हैज, which is already having orientation very similar to the applied field, that keeps on growing until a single domain is observed, and then this single domain undergoes a tilt, a rotation to align. So अब देखिए ये जो फाइनल आप देख रहे हैं यहाँ पे, और ये दोनों अलाइन हो गया है. So that is what happens at this point. जो जस्ट सेचुरेशन, सो ये जो पर्पल कलर में दिखाया है ना, पिंक कलर में सॉरी, जब तक जो सेचुरेशन अचीव कर रहे हैं, तो ये जो पॉइंट है जहाँ पे धीरे से हल्का सा स्लोप इज नॉट दैट मच. ओके, सो दैट इज द पॉइंट वेयर रोटेशन हैपेंस. और ये जो पॉइंट जहाँ पे स्लोप ज्यादा आ रहा है, दैट इज द पॉइंट वेयर डोमेन वॉल मोशन इज हैपनिंग, एंड दिस इज द पॉइंट वेयर डोमेन, ये वाला और बाकी सारी चीजें, ये बहुत इंपॉर्टेंट है इसको, कि वो जो हम ग्राफ देख रहे हैं उसको क्या समझ रहे हैं कि अंदर में क्या हो रहा होगा उसके अंदर. डोमेन्स हाउ, सो दिस इज द डोमेन रोटेशन ऑफ द डोमेन. सो दैट्स domain rotation. So two things sequentially, that this is what happens. So now we can focus on the wall. ये जो wall है ना, domain wall. So there are two domains separated by a wall. और उस wall को अगर हम thickness को देखें उसमें कैसे, so ये एक domain है. We are focusing on walls now. डोमेन वॉल, तो उसको जूम इन कर रहे हैं. जो एक लाइन हम यहाँ पे दिखा रहे थे, सो वी वर शोइंग दीज एट वॉल्स एज लाइंस. सो दिस वाज आवर वॉल, दिस इज द वॉल दैट आई एम टॉकिंग अबाउट. जो बाउंड्री है दोनों के बीच में, उसी को हम वॉल कह रहे हैं. ओके, सो दिस इज आवर wall. So let's zoom in to the wall. So wall के इस तरफ upspin, and the other side we have downspin. So there are collection of, there are lot of spins which are arranged. So we are looking at the, so there must within the wall, if the atoms would have spins which will be gradually tilting, it will be gradually changing in this manner. Okay, so this change in the, so this is the entirely upspin, this is one domain, domain 1, and this is the domain 2. So on this side of the wall you have upspin, on the right hand side of the wall you have downspin electrons on each of the atoms pointing in downward direction like this. So this is the thing that we see. So within the wall there must be a changeover. So बीच wall के अंदर जो आपको दिख रहा है कुछ atoms होंगे जिसपे boundary हम बना रहे हैं. So within the wall there must be a change, gradual, there must be change in the this like this. So completely from the upspin to slightly making this kind of angle, and finally making downwards tilt. So this is what this kind of wall is called a Néel wall. So here what we have shown is that अगर spins आपके screen के parallel हैं, मतलब उसी में up या down है, तो within that we are showing how it is tilting. But the same thing can happen जो screen से बाहर आके भी change हो सकता है, मतलब the component of the spins that you see here. So in this case the tilt is happening because there is a change in the spins, it is in getting changed, but the tilt, this change in the rotation, this spins is happening gradually. It is the coming out of the screen, the direction is out of the screen, and that's so there are two types of wall, Néel wall and block wall, depending on how so this classification is based on how the spins reorient within the wall. ठीक है, the wall which exists between two domains, there must be a changeover from the spins on the domain 1 and spins on the domain 2, and for this changeover there should be a gradual change of the direction of the spins. And so if the direction changes within in the same plane as shown in the picture, then that is nil wall. And block wall is if the change happens gradually coming out of the stream. If the vector starts pointing in this direction, there's a component which is uh, it can start tilting coming out of the plane, and gradually the component in the plane will decrease, and gradually you will have zero components. That can also we can think of. Okay, so ferromagnetism is ferromagnetic materials is understood. There are several theories, but there is one model which can be understood through Stoner model, which is most. So this model is nowadays better and used for understanding ferromagnetism as compared to other models. This uses the band theory to understand, and some part of it I have already explained in previous classes on metals: iron, cobalt, nickel. So a non-magnetic metal will have equal density of states for spin up, spin down electrons at the Fermi level. There is no effect. Whereas when you, so let's go to the part here. So this is what, for a normal metal which is not magnetic, you have equal densities, equal uh, density of states for the upspin and downspin, equal density of state for normal metals. But if it is ferromagnetic, then there is split that happens, and similar to what I told you in case of electrical conduction and electric fields, here it is the magnetic field that has been applied, and in this case what happens that there is a split of the bands. So if the field is applied in the upward direction of applied field is upward. So H I was indicating by H, so I should write H. So this is the applied field. uh, if suppose this is the applied field, then in a ferromagnet what will happen, the spins which are aligned, they will have lower energy. They will have the density of states, so the overall bands will split, and more electrons will be coming to this side, and so this energy that you see, so they are more stabilized. The density of states of this type here, less density of states at the Fermi level, less here, high density of states. So that is what you can see. So there is imbalance, and because of this there is overall magnetism that you spin. So majority spins which parallel to the magnetization. So if H is applied, the applied field is upwards. The so the yellow shading increases. There is greater population of this band. There is also less density of state uh, for the spins that have been aligned with the thing. So overall the energy has decreased. So there is overall decrease in energy. What we see here, that in such cases overall energy decreases. So this is what happens, and that's why these ferromagnetic materials uh, behave. They show overall magnetic behavior, that they that we know as for now. So if you are able to calculate, I shown somewhere that you can calculate the number. If you observe the total magnetic field, you can actually, sorry, mouse pad काम नहीं कर रहा है. So I told you earlier somewhere that you can easily calculate the number of spins. Okay, yeah. So yes, so the magnetization is related to the number of yes, magnetization that you can see is you can calculate number of unpaired electrons. So and you can easily correlate that with the thing. So this was the thing that we earlier discussed in previous classes. So like NB, so you practically you measure the magnetization value and compare with the, put it in the formula, you both magneton is fixed, and so here you can see 7 electrons in F, so 6.8, so something like this you can get, so very close to the value. So now uh, what we are discussing here, coming back to the slide here, sometimes that you get, so हाँ, अब जो हम यहाँ पे देख रहे हैं नॉन इंटीग्रल वैल्यूज इसकी क्यों आती है, 7 वहाँ पे क्यों नहीं आया, 6.8 आया, या कई बार उससे कम भी आता है, फ्रैक्शन में आता है. So why we get non-integral value? So the reason will be that it is because of coupling of things, spin momentum, spin angular momentum with orbital angular momentum, and magnetization of the conduction electrons, and ferrimagnetism. So these three. So ferrimagnetism is something that we will discuss next. So non-ferromagnetic magnets, that chromium, bromide, europium oxide, europium sulfide. So ferromagnetism we have already discussed in the band model earlier. Here is just a similar thing, that is, so in copper is paramagnetic, 3d10 4s1, and so you have completely filled d bands. In d band you have complete filling, so half of the band is filled with 5, so up spins, another half you can expect down spin. The nickel is ferromagnetic because of the vacant spaces here. So initially, which is you see here that 3D, in the absence of field, in the absence of magnet, so when you have temperature greater than Tc, then it is equal filling of the 4.7, so it's holes here. But when you have temperature less than the Curie temperature, that is the point where you get to see the spins are ordered. At higher temperature, the spins try to, because of the thermal energy, they get randomized. So less than this temperature, you see an ordering, and there is high one type of so you have one type of spin is less in number and other one is higher in number. So this is the kind of band split that I was trying to show earlier in the picture. So in the magnetic field, so this kind of thing happens in case of ferromagnetic materials. Now there is another important type, is ferrimagnetic. materials and quite useful. Normally the Fe3O4 is example of ferromagnetic uh, magnetite. We call it magnetite, demonstrated by uh, magnetite is the name given to Fe3O4. Typical example of ferrimagnetism comes from this, which is basically Fe2 mixed oxide. This is a Fe3O4, which is a mixed oxide. So it is a mixed oxide. Example of a mixed oxide. So मिक्स ऑक्साइड में हमेशा ये होगा कि एक 2 और एक 3 ऑक्सीडेशन स्टेट में होगा, दो तरह के ऑक्साइड होंगे, और एक +3 में एक +2 में ऐसा होता है। तो इस केस में फेरी मैग्नेटिज्म अराइज करता है। सो टिपिकली इन फेराइड्स विच आई टोल्ड यू, सो मैग्नेटाइट्स को जनरलाइज अगर हम करेंगे तो फेराइड्स ऑब्जर्व्ड इन फेराइड्स कहते हैं कि दिस इज अ फेनोमेना which is typically observed in ferrites. So, okay, फेराइट्स किसको कहते हैं, जिसमें यूजुअली जैसा अभी हमने देखा एक ए होगा और Ab2O4 +3 ऑक्सीडेशन स्टेट। सो यहाँ पे Fe2 एंड Fe3, सॉरी +3 ऑक्सीडेशन स्टेट में होगा। So that was the structure that we were getting. So in general, this is what you called Fe3O4. Okay, so ferric ions greater in number, double the number of ferrous ions, and that kind of solid structure if you build with oxygen, making the closed pack structure in which uh, iron get iron 2, iron 3 plus 3 plus 2 occupy the octahedral and tetrahedral sites, that the void spaces that you have. So those holes are occupied by these ions. So that is the structure of ferrimagnetic material. Typically this ion that we are talking about uh, can be different. Okay, so anyway I can just discard these things and then we can have this. Okay, so yeah, ferrimagnetic. So what I was talking about is the ferrimagnetism is that so simple. So you have two lattice sites, uh, tetrahedral, octahedral sites, where the two different types of +2 and +3 charged ions can interact. Their spins can interact through the oxygen. They are separated by oxygen atom. Two metal ions separated by oxygen within the lattice structure, A and B lattice sites, and the exchange interaction, the spin exchange occurs through oxygen and ion, and this particular behavior is called super exchange. If two electrons change their spins uh, with the help of oxygen atoms, then which are in between them, then this interaction is called super exchange interactions. So that is a typical thing that is observed in such materials. So on so there are two lattices, so there is anti-parallel alignment of some of the spins. We'll see how that happens. uh, and the A and B sublattices have different uh, spins, and because of that you have, doesn't cancel out, and you have net magnetic moment. So when you observe the thing M versus H curve, it will look almost similar to the ferromagnetic material. So ferromagnetism is when you perform behavior, magnetite is a material which is highly, you bring a magnet, it will be particles of magnetite will be strongly attracted to a magnet. So the behavior is almost similar. Practically you cannot distinguish between the two just by looking at two materials. Only if when you do a very detailed crystal analysis, structure analysis, then you are able to know whether it is due to ferromagnetism. So behavior is similar, ferromagnetism and ferromagnetism. And it will also have spontaneous magnetization, hysteresis, remanence, or remanent magnetization. All these things will be there in case of ferromagnetic materials. But what we find is that they have different magnetic ordering. In case of ferromagnetism, you have both. There it is split there are two types of sublattices, or which have opposite spins, but they do not cancel out. So something like this happens. So this was something discovered in 1940s with magnetite. It was the first ferrite that was discovered and understood before. So because of this similarity between ferromagnetism and ferromagnetism, magnetite was considered to be ferromagnet in until Neal gave his theory in 1940s and the correct theoretical framework emerged. So that is so magnetite is a ferromagnetic material, but it was considered to be ferromagnet because there was no understanding of the properties. There was no theoretical framework till that time, and the behavior is similar. So you do not. It is difficult to distinguish practically. So Fe3O4, the example that we are going to discuss in detail is the spinel structure. Oxygen undergoes close packing, and the voids that are created amongst with the close pack structure fill the voids. The iron fills the void. The tetrahedral site, where it is surrounded by 4 oxygen, the iron gets surrounded by, whereas at octahedral site, iron gets surrounded by 6. So we call this as two sublattices from the magnetic point of view. That these tetrahedral and octahedral sites are two sublattices, the metals that occupy these sites, and we label them as A site and B site respectively. Tetrahedral is A, and octahedral is B. So that's how we label this. And the spins on A are anti-parallel to those on B. So those two lattices, and so the distribution is like this. The Fe3 plus gets distributes itself. Half of the Fe3 plus occupies the A site, that is the tetrahedral. So it goes into the tetrahedral, and half of it is here in the octahedral site. So site A and B that we see, A for tetrahedral, B for octahedral. So Fe3 plus gets distributed in both the tetrahedral and octahedral sites. Fe2 plus occupies only the octahedral sites. Fe2 plus is bigger in size, so it is in octahedral, and Fe3 plus can fit into the both. Okay, it is smaller in size, the ion, and so you can have this kind of structure. So this particular type of structure in the exists in the magnetite, and this is what we know as inverse spinel. This type of arrangement is called there is net magnetic moment emerging from the exchange interaction mediated by oxygen. So you see this structure, oxygen is this. So oxygen is here. So this is the A site, labeling of the A site. So tetrahedral. So you can see this, the tetrahedral. If I may ask you to look at this site, look at this. If this is the tetrahedral A site, and the B site, it is surrounded by you can see, look at here, 6 octahedral site where it is surrounded by 6 oxygen atoms. Tetrahedral 4 octahedral. So what we learned, that Fe3 plus gets distributed in both A and B sites. Fe2 occupies the octahedral site. So this octahedral site, you will have both Fe3 plus as well as Fe2 plus, and here you have only Fe3 plus. So half of the Fe3 plus goes to the A side, half of the Fe3 plus ions goes to the total number of ions. If you have say 100 ions of Fe3 plus, so half of it will go to A, and another half will go to B side. Okay, so ferrimagnetic order can be understood through this way when you calculate the parallel spin. So if it is a D5 system, Fe3 plus, and so you have 5 by 2 is the total spin that you calculate, whereas Fe2 plus you have S is equal to 2. Okay, so it is a D6 system. So when you calculate if the spins are aligned, total you will what should be the spin if all the spins are aligned. 5 by 2 here, and 2, and plus you have from Fe2 plus you have 2. So total you should get total number of electrons that you should get is by your calculations should be 14, all of them aligned together. Okay, number of electrons, but this value is never observed practically. What you get is that because site A is tetrahedral, sorry, this one is wrongly labeled. Site A we are calling for tetrahedral. Labeling mistake here. Tetrahedral. So tetrahedral is filled with Fe3 plus ions, and octahedral sites you have uh, yeah, what is happening here, this labeling. So there is something that we can, just a moment. There's something wrong. Okay. So this was, so this is what I was saying, that you have two things here. Octahedral sites So the tetrahedral site is filled completely with Fe3. I will correct it later. Yeah, this is tetrahedral. That's what I was highlighting. Oh my god. And you have octahedral sites, the B sites, where Fe3 plus ions are there and Fe2 plus ions are also there. So what will happen? So you have this is upspin at A site. It is all upspin, whereas on the B side, all the whether it is Fe3 or Fe2 plus, they are all downspin. Okay. So there are you can count 1, 2, 3, 4, 5, 6. So you have total of so all the spins are here. You can see corresponding to S is equal to 5 by 2. Another set of S by 5 by 2, but it is pointing down, and S is equal to 2. This is pointing in the again downward direction. So overall the Fe3 these two will cancel out. Upspin downspin. The only so overall so this gives rise to overall magnetic behavior that you observe due to the Fe2 plus ion that remain that have uncompensated spin that is not getting cancelled anyway. Okay, so Fe3 the magnitude of the total spin angular momentum spin magnetic uh, moment gets cancelled out for Fe3 plus in A and B sides because they are anti-parallel, and Fe2 plus remains. So that's the thing uh, which tells us. So that is the key to understand this kind of behavior. So we have cancellation in these two places. Cancelled Fe3 at A site and B site getting cancelled, and finally you have so this kind of behavior is typical for any ferrite. Any ferrite will show this kind of behavior, metal oxide and Fe2O3. So combination of these two oxides where M can be zinc, cadmium, iron, nickel, anything. So it is when it is iron we call it magnetite. This is a special case. They are poor conductors and good for transformer cores. So this is a picture of the spinal structure. So there's three important points that I will focus. There's a lot of sometimes if you read books and they give you sometimes wrong interpretation of the curves, so you have to be careful about this. There's a so there are two types of curves, M versus H or B versus H. There are two types of curves that can be plotted. One is to show M versus H, or so both curves are used to explain the magnetic behavior. But what is the difference? M stands for magnetization. So magnetization induced as a result of applied magnetic field. So it is the summation of the magnetic moments over a given volume, over a given set of mass, total mass of the substance. Then what is the B versus H curve? B versus H is the curve that represents the magnetic field produced, strength of the internal magnetic field that is produced. So B versus H, if it is plotted, it will be the internal through the substance, उसके अंदर कितना magnetic field है, internal strength of the internal magnetic field. So that is plotted as B. This is given as B. Okay, so B, and so this B, the internal magnetic field will be sum of the two factors. One is the external field, externally applied magnetic field mu naught H, and and due to the internal, when the spins are getting aligned, it is producing all the spins. So that is additional that will contribute to. So each of these magnetic moment will have also generate magnetic field, right? So this additional field is due to the magnetized sample within the sample that has been created. So the two, so total magnetic field is the sum of the two factors. One is the external field, and this is due to the magnetization. So the spins that get arranged. So both these factors lead to summation of these two is leading to the overall field that is produced. So that two important points is that whenever you plot M versus H, the red curve, look at the red curve, it will saturate at some point. That when all the spins are aligned, you cannot have the change in magnetization, and so there is a point where no change will occur, and that when you look at this point, the slope is 0. Okay, but if you are plotting B versus H, so see, mu naught H, as long when H increases, the mu naught H term goes on increasing in a straight line fashion, and it never saturates. So when you are summing it up, mu naught M plus H, it will also show a non-saturating behavior. It will go like this, never saturates. So B versus H, it will never saturate, because as long as you are increasing the external field, that mu naught H will go on increasing. But M versus H curve, if you are looking at this, it will saturates at some point. So the nature of curve that you plot will show a plateau like region, a flat region when you are rising at the top, and after that flat. But when you are plotting the total magnetic field produced inside the substance, which will be a sum of both the things, the magnetic field due to the alignment of this spins, and the magnetic field which is externally applied. So both these are contributing to the internal magnetic field. So this external field is a straight line behavior, it will never saturate. But the field that you have, a magnetic field that is produced due to the spins aligning itself, so that will have a limit, because once you have limited number of atoms, limited number of electrons in a substance, so when all of them have aligned, they are pointing in one direction, then there is no further change that can happen. So there are two things. So we discussed two things: magnetizations, which we were talking about initially, and it will, so you can see always a saturation here that I was talking about. But when you plot this B, magnetic induction, we call it B. B is the magnetic induction that represents the total internal magnetic field that is produced as a result of application. So this is called magnetic induction. So there are two types of graphs which are uh, usually referred to for understanding magnetic behavior. So magnetization is the more appropriate one to understand the behavior first initially, and then you can refer to magnetic induction sometimes. So the plot looks similar but not exactly the same. In case of magnetic induction, there is no saturation. Here you are getting saturation. uh, in this case, no saturation is there. So when you plot, so that is, it is going on increasing. The direction you see, it is like this, no saturation, it is going on like increasing forever. And so here when you plot d slope, what was the slope here? Slope in the magnetization case, you got magnetic susceptibility. So dm by dh was susceptibility. This was susceptibility, but this dm by db by dh will be called permeability. So db by dh, this is the slope here, and this slope is permeability. Okay, so permeability and susceptibility you should be able to distinguish when you plot the magnetic induction or the internal magnetic field versus H. Then this is the net result. Incremental permeability is the slope at one point, incremental susceptibility is the slope at any given point. So this is the increment susceptibility slope here. Dotted line shows the slope at different points. So this is the incremental susceptibility, incremental permeability, and when you are measuring it over an area, then it is called apparent permeability, or it is called apparent susceptibility over in a range. So this is the point to be distinguished between magnetization curves M versus H. H saturation, magnetic field, the at where maximum value the saturating no more changes in magnetization occurs. So that is H saturation MS HCI. This is the coercive field in the negative direction where the force becomes zero. Magnetic remanent magnetization, this is the magnetization that exists in the substance when the field is zero. So these are the points. Similarly here you have the value of remanent induction. This was remanent magnetization. And this is the remanent induction. So this is called remanent induction, remanent magnetism. So parallelly nomenclature is there, but the difference what you are seeing here is that it is consistently in B versus H curve there is no saturation, and it is constantly increasing. It is never stopping, but in this case it is saturates and there is no further increase in the magnetization value. So that's the point to be distinguished. Magnetic anisotropy is as the name suggests, anisotropy means that if you get a property, if you measure a property along different direction and you get different values, so that is anisotropy. So here we are talking about the magnetization value along different crystal axis, different crystal directions. So that can happen in some cases. So there are three types of anisotropy that can result. There is one magnetocrystalline anisotropy that arises due to the change in the due to the internal structure of the crystal itself. So there is a pattern, certain number arrangement of atoms is there, and because of that there will be a behavior. If you apply magnetic field along certain direction of in the crystal, along the different directions, you will get different values. So that is anisotropy. If you are getting the same value irrespective of which direction you select, same value of magnetization along different directions, then that is isotropic behavior. Okay, so magnetocrystalline anisotropy is due to the crystal structure. This kind of behavior can also arise due to the shape of the particle, whether it's rod-like shaped or spherical shaped, cube-like shaped. So depending on that structure also it can arise. And then third type of anisotropy can arise due to stress. So in this semester we are only focusing on the first one, the magnetocrystalline anisotropy. Anisotropy which arises due to in crystal structure. Rest two is not to be at this point of time. I am not going to discuss. So magnetic. So most important is the first one, magnetocrystalline anisotropy. So this is so it affects the shape of the loops, controls the coercivity and remnant magnetization. It is also important in defining for various devices. So this is the behavior. So when I talk of magnetocrystalline and anisotropy, this pictures sums up the whole thing. So this is the magnetite crystal Fe3O4. So you have 100 crystal direction, 110, 1110. So there are three different crystal directions. We discussed what is the crystal direction earlier in previous classes. So you know this already. Crystal directions. So we have three different crystal directions. Now it is labeled as easy, medium and hard. So this is what it means is that if you apply magnetic field along say 111 direction, you get a very high value of magnetization. Even if you apply less field, you get high value. So you can see the difference here. So suppose we are applying, gradually changing the magnetic field and applying it along 11100 and also analyze it at 100 and also analyze it at 111 direction. So 111 direction is the blue line that we have obtained. So the change in magnetic moments, if you follow this, so you see you get a larger value of so the curve shows that it is easier to achieve a magnetization in the direction of 111 crystal direction as compared to 100. So these are the 110, these are the Miller indices that you already know. So perpendicular set of so you have parallel planes, set of parallel planes, and perpendicular to that if you draw an arrow, that's your crystal direction. So along 111 axis, if you apply magnetic field, you see you get a high value, much higher value of the slope is different here, and you are getting the saturation magnetization is achieved at a smaller value of uh, external magnetic field. Okay, whereas for the same achieving the same saturation magnetization, you have to apply a much higher value, almost 3 times the higher value in along the 111 direction. So there is in some this magnetite Fe3O4, we are talking about Fe3O4. So it has a property that if you apply magnetic field in aligned with the 111 axis or 100 axis, the behavior is different. Along 111 axis, there's greater sensitivity. There's for the small change in the external field, there's a there's a greater change in the magnetization value, and so it approaches the ms, the saturation limit varies early, whereas along the 100 axis it is difficult to magnetize and you get the saturation value later at a much higher value of uh, externally applied field. So we call it easy direction of magnetization, when we are achieving the saturation magnetization very easily, very quickly, by applying a less amount of field. And when we are applying a much higher value of applied magnetic field, and then only we can get this kind of saturation. So that is hard direction, it is difficult to hard. So these two axes has to be identified in a crystal. And so this is an intrinsic property of any ferrimagnetic material. Just a moment. So just Zahira, just a moment, please. So 111. So what we find here, that along 111 direction, there is easy direction of magnetization, and 100 is the crystal direction, which is called the hard direction of magnetization. Okay, so and there is intermediate between them is the 1 behavior of 110 direction. So so this is what we mean by anisotropy, magnetocrystalline anisotropy. So by measuring the magnetization along different directions, when we apply magnetic field along these three different directions, we get different behavior, and that is what we understand. So this difference in energy, the energy required. So if you uh, have something aligned to the easy direction of magnetization, and then you suppose try to change the magnetic moment to the hard direction, so you'll have to spend some energy, you have to give some energy to the system. So that energy is magnetocrystalline anisotropy energy. So this magnetocrystalline uh, anisotropy energy is the energy required to deflect a magnetic moment in a single crystal from the easy to hard direction. So so easily जहाँ जिस डायरेक्शन में मैग्नेटाइज हो गया है उससे डिफ्लेक्ट करके आप जो दूसरे डायरेक्शन में है उसको चेंज करना चाहते हैं, विच इज द हार्डेस्ट in that crystal system, that is called, so some energy that is required, that is called magnetocrystalline energy. So दोनों system में, so there is energy difference between the two, aligned with the 111, aligned with 100, so that difference is your magnetocrystalline energy. So easy and hard directions arise from spin orbit coupling. Okay, and as I told you, so these are the atomic dipoles. So this picture tells you sums up the whole idea about the magnetism and domains and walls. So these are two domains here. One domain, what you see here, two domains here, because they are individual atoms with spins pointing in the different directions, and in between, so net summation of these two, all the spins is shown here. Okay, with a thicker arrow, bigger arrow pointing in this direction, whereas so this is shown here, and this overall thing is also shown here. Okay, so this is the way. So now we are zooming into the wall. This dotted line represents the wall, and what is how the wall is what are the arrangement of spins within the walls, atoms that lie within that wall like a dotted line. So when we zoom in, we get the microscopic picture that they tilt from, say, initially it was north south direction in the upward, so that was the domain 1, south to north direction in the domain 2. So within the wall you will have a change from north south to south north direction. So upspin to downspin should occur within the wall. Okay, now let's consider the domain formation, why domains are formed initially. So we'll answer this question when we understand a few more points. We should be able to answer that why domains are formed. So here, first picture on the left hand side is a single domain, you can see, and on the right hand side we have two pictures of the multi-domain thing. Amongst that you have, so single domain in one, then two domains, and then so gradually we are increasing the number of domains. So so what happens here is that, so this there is, when something like this happens, what is happening here is that due to the magnetic field, uh, some of the charges within the electrons will tend to move. They feel electrons have magnetic moments themselves, and because of that they will get accumulated to one part of the, so electrons get accumulated due to the magnetic field on one side. So one part of, so depending on the direction, so ये सब electrons occupying, electrons are getting, due to the magnetic force, the electrons are accumulated to one part of the crystal, so other part acquires a positive charge. So there is what happens because of this. In this structure you will have, this will be another source of magnetic field which we call as demagnetizing field. And so this expression is the, so this is another source of field which is internally generated because of the interaction between with the external force, external magnetic field. So this is a demagnetizing field that is generated. It is in the reverse direction to the applied magnetic field. So if the field is applied in this direction, so if external field was pointing in the up direction, you have, okay, so because of this kind of charge separation that occurs because of the magnetic force acting upon the electrons, if you have two domains, they are so if you have one domain, then they are separated by a large distance and the energy of the system is high. Now look at this picture on the right hand side. When we have two domains, a similar thing will happen, but there will be partial. So when there two domains exist, the electrons in one of the areas are accumulated to this side, whereas in the other they get accumulated to the other side, because the magnetic field now acts differently. एक अप स्पिन है एक डाउन स्पिन है, दोनों पे डिफरेंट डायरेक्शन में लगेगा. So electrons, because of the magnetic field, are now, in one case they are accumulating here, in another case they are accumulated to the other side. Now you see the charge, the two charges, the plus and minus, are very close to each other, and so the overall energy of the system is low. When they are widely separated, the plus and minus charges are separated by a large distance, as in the first case. This so the charges are accumulating but in a different way here. So plus and minus, this difference is closer. Battery. So plus and minus, plus and minus, they are closer. अरे चलता है कभी नहीं चलता. Closer, energy will be less. So if you now increase that thing, then the separation, so but here the distance was more, plus and minus in the first picture, so the energy was greater. Now if you split it further in the third, in the three domains with 180 degrees in reversal of spins in one by one, so this is the situation. Then you have charge separation, plus and minus are still get further closer, and the energy, so because of this, so as you increase the number of domains, the overall energy of the system decreases. And so there is a natural tendency to have multiple domains in a system. In a single domain you have this kind of structure. The plus and minus charges, uh, due to the magnetic force that acts upon the charges within the crystal, so you have electrons as the charge carriers, and which are easily highly mobile, so they get accumulated to one side. And this energy that you that is developed, that due to this kind of charge accumulation, is called magnetostatic energy. So the magnetic force, application of magnetic force leads to accumulation of charges, and because of that the energy, so that is called magnetostatic energy. So so that now we should be able to answer why domains are formed. So following reasons, so reasons that we just picture that we have just seen in the previous slide. A single domain, compare with a single domain where you have uniform magnetization, there will be surface charges will be at the ends, towards the end of the two. Okay, whereas so surface charges develop at the two ends due to the magnetic force acting upon them, and this, because of this accumulation of surface charges, there is another field that develops, that is demagnetizing. It is opposite in direction. So what I want to say, that it is, if you are applying field, my stylus is again not working. So if you have it acts as a demagnetizing field, it is in the opposite direction to the applied field. So energy associated with this kind of surface charge distribution is called magnetostatic energy. So this magnetostatic energy has to be reduced for system to be stable, and for that, if you divide it into multiple domains, then you take the summation of all these interactions between with the accumulation of charges, and which is due to the this thing. Uh, so if you have two domains in opposite direction, then plus and minus charges are closer to together, and because they are closer together, the overall extent of the demagnetizing field is less, and so overall magnetostatic energy will decrease. So when plus and minus charges are closer, the demagnetizing field is less, which is shown in the previous picture. Demagnetizing field acts between this and this, so that is goes on decreasing gradually, and there is this thing. So division, so more and more divisions within the domains, and creating more domains lead to uh, lowering of energy, but there is a limit. ऐसा नहीं है कि infinite number of domains will give you infinite a very good stability. No, that will, so there is a limit to it. So there's another factor that counteracts, that acts against this subdivision into multiple domains, and that is the wall energy. There's certain energy required to create the wall, because the at the juncture you have walls, which we can consider to be, it can be wide or thin, depending on, so there are two types of wall that can happen. So remember, domain 1 and domain 2. So domain 1 pointing in up direction, all the spins. In the domain 2 you have all the spins pointing in the downward direction. So within the wall there must be a changeover. Now the changeover from the up spin to down spin can occur through uh, either gradually, so gradual change in the spin change, or it can be abrupt change. The change in the can be abrupt, and very surprising. So abrupt change, or, so I'm not able to write here. So कभी काम कर रहा है कभी नहीं, so दिक्कत हो जा रही है मुझे. So abrupt change. So abrupt change of the spins of spin. So within the wall, the magnetization must change direction. That is the important. Within the wall, the magnetization must change direction. So the change can happen gradually or it can be abrupt. So if it is gradual change, you get a wider wall. If it is an abrupt change, you can get a thin wall. So what is the uh, energy consideration into this? Wide and thin. So we have also talked about magnetocrystalline energy earlier in case of magnetite. So different directions, different magnetization. So there is a tendency of the spins, if the spins are aligned along the easy direction of magnetization, that will give you low energy. So uh, domain walls always have finite width, and that is the consideration of two things: exchange energy and magnetocrystalline energy. So both these factors determine how wide or thin your this is to be going to be. So so when we have this kind of the two things that we are talking about, gradual and abrupt change, as in B and B picture. So what is the difference between how we consider this? So when there is abrupt change in the spin, so there is a sudden loss of exchange energy. Exchange energy was there between the parallel spins, and suddenly that is lost. So there is a huge loss of, so when the spins up, when you keep the spins parallel and suddenly you lose it, then there is loss in exchange energy, and that loss in exchange energy can be minimized if this if the change by 180-degree happens gradually, the first case. So gradually over many atomic units. So these are all different atoms. Over several atoms, the spin is finally changing to from upspin to downspin. So there is a gradual change, and you have less, the loss is minimum. But when you have abrupt change, so when you have, so loss in exchange energy energy is is minimum. So you need to minimize the loss in exchange energy, whereas in the second case, here loss is more. Loss of exchange energy. Exchange energy is a negative term, you know, it leads to more stabilization. Exchange energy loss is minimized. Here it is greater loss. Loss of exchange energy. So loss in exchange is minimum. So in one case you are when you are changing it gradually, you are minimizing the loss in exchange energy, but when you are doing it suddenly, changeover is happening suddenly, there is greater loss of exchange energy. But there's also spins within the walls. So you also note that the spins that within the walls are not aligned along a particular easy axis of magnetization. So so because you have so many orientations possible in a wider when the gradual changeover happens, so there is a magnetocrystalline energy is high. In that case, there's so many different orientations of spins there. So magnetocrystalline energy is high in case 1, wider wall, but it will be low in the second case. So there is but all these factors determine what should be the leads to a concept. So when you consider all these factors, you find that factors which are acting in opposite manner, and so there some you have, if there is so you have a finite width of the walls. It cannot be like infinite, and so for the same reason you can have only certain number of domains which can be formed. You cannot have infinite number of domains formed to minimize the magnetostatic energy. So mainly you try to minimize the magnetostatic energy initially, and that you got multiple domains are good, you said. But when you are creating multiple domains, you have to create walls, domain walls, and these domain walls uh, depends on two factors: exchange energy and magnetocrystalline energy. So exchange energy tends to make the wall wide, as wide as possible, because uh, yeah, there's a gradual changeover from the spins, and so the as you know, if they are kept as parallel to each other, there's good exchange energy, and which is lost. So slow changeover, slow loss of the energy, uh, exchange energy. So exchange energy tends to make the wall wide, जितना gradual हो सकता है उतना करने, but anisotropy of the system tends to make the wall thinner. So these are the two opposing factors, because anisotropy will like of the system will like that everything gets oriented along to a particular easy direction of magnetization. So as a result of competition between the two factors, uh, exchange energy and anisotropy energy, the domain wall has a finite width on the order of 100 nanometers, and so you have certain surface energy. So I think we so this is the thing for today, and yeah, no, a few more things and then I'll like to finish this topic. So I straight away go to this part. Okay, so few more points and I'll be done. So now look at the, if you analyze different ferromagnets, you will get different types of, so image versus curves varies in different manner. So there are certain ferromagnetic material which have high value of magnetization. So you can see you apply a very small amount of magnetic field, and you achieve the saturation value, saturates very early, and it also has high remanence. In the first case, large remnant magnetization. So you see MS and MR So MSMR that you see, so MS, so you look at these points, so they are close to each other. So this is uh, it has, so what is the, so such, the left hand side that you are seeing is the picture that is what we call them as hard magnets. That is, they have once magnetized, once you apply a magnetic field, they will achieve the saturation magnetism very quickly with an application of a low uh, magnetic field, and then they retain their magnetization to a good extent. So these are large remnant magnetization. These are good for making recording media, memory devices. These are good, they are made, so they are hard, and there are certain things. So hysteresis loop is very big, that you can see here. The loop area is big, and they have a high value of coercivity. I cannot mark it. So see, this HC is large. Negative direction of the magnetic field is large in magnitude. You have a tough time bringing the magnetization to zero in this system. Natural tendency to have a high value of magnetization. This is good for recording devices. On the other extreme, you have something like this, where it is, the loop area is small, and what you see is there is a huge difference between the MS and MR. Okay, so it is not able to retain the much of the values, much of the magnetization which was in the presence of field. When the field is removed, it loses much of the magnetization. So these are not good for recording media. When such ferromagnets, these are soft, these are also called soft ferromagnets, but they are good for transformers and motor cores to minimize the energy dissipation in AC field. Okay, and this loop area, that is important. It tells you about the dissipation of energy when the field is repulsed. So positive direction of magnetic field, negative direction, when you reverse the field, there is energy released. So energy dissipation that occurs, how much energy will be dissipated, that you calculate from the loop area. So two extremes, two things: high value of remanent magnetization, that is, and high value of coercive field, that is the case of a strong magnet, which is used for making permanent magnets. So that is, so soft ferromagnetic material and hard ferromagnetic material, this is the difference that I was talking about in the previous slide as well. Soft and hard. Soft one is having less HC, less value of MR, and as compared to hard magnet, you have large coercive field, coercive force is required, and it retains much of this, the saturation magnetization, as compared to saturation magnetization, remnant magnetization only little less. It is retaining most of the magnetizations even after the field is removed. So that is hard and soft. This is the difference you should understand. Okay, it is the difference between HC and so put in one slide. This is the thing: soft one having this kind of loop, hard one having a bigger loop, and so that's it for today. So in actual sense, there is much more different. So it is actually appears like this. That is slightly exaggerated here to show that you get the features correctly. So that's all for today, and we are done with the magnetic materials. We are not going into spin waves. I am not going to do this time. Okay, spin waves is there in the slides, but that is okay. We can do that. So that's all for